functions and what it means to be a function. When we talk about functions, I think most of the time we think of graphs and stuff, but functions can be applied to a whole bunch of stuff, and we'll see that in a second. We're going to apply it to a real-life mailman function. But a function, it's just a relationship between two sets called the domain and the range, in which the domain is paired with exactly one element of the range. When I think of that, when I picture that, I picture I have a whole bunch of elements in a domain, and they actually get mapped to an element in the range. To get mapped to something, you only get mapped to one thing. Like me personally, I only can walk into one classroom at a time. I can't walk into two classrooms. That is why each element of the domain can only go to one element of the range, because you can't split apart those numbers to go in two different places. But the long and short is just this one sentence here that says, in which the domain is paired with exactly one element of the range. With graphs, we're always going to use that vertical line test. And anytime I see vertical line test, I go ahead and picture what it means. We'll talk more about it in a second. But that vertical line test, all we're going to do is I'm going to draw two graphs down here. I'll draw one here, and then I'll draw one here. All the vertical line test is you just put a vertical line all the way through the graph, and as long as it hits one point at a time, it passes and is a function. So, for example, on that one that looks like a U, no matter where you put that line, it's just going to intersect at one point. So that means that passes the vertical line test and is a function. On the other one, however, pretty much anywhere you draw a vertical line, it's going to hit twice. That's more than once, so that fails, and it is not a function. We'll talk more about that in a second as well. I just want you to realize, because I very briefly talked about the vertical line test, and everyone's like, oh, we've seen that before. Then we got to the test, and about 8 people got it wrong. Don't get this wrong. Sometimes I feel like I graze over stuff, and you're like, I don't need to study that. Know it. Practice it. Take it seriously. It will be on the test. All right. So I find that people get kind of mixed up on what a function really is with that definition. So I apply it to a real-world thing, and that is a mailman delivering mail. Now, when you have a mailman, we all know what mailmen do. They have a bunch of letters, and they take those letters and they put it into a mailbox. So we're going to go ahead and draw what's happening here. It's going to be a great, fantastic drawing. This is going to be my mailman. That's his head. There we go. That's a leg. He's walking. Obviously, the mailman walks. And maybe he has a little mailman hat on. And we're going to really know he's a mailman because he's carrying a big bag.
It's a merce.
That says mail. No, it says mail. It's obviously a mail bag. And what he's doing is he's taking...
It's a mail bag, so it's a man purse.
Yeah, it's a merce.
He's taking envelopes.
Yeah. It's a college acceptance letter. The big envelope. Yeah.
And he's putting it into mailboxes. Quit making fun of my mailman. Jeez.
He's in the air.
He's just going to throw it in there. He's really good. It's just... He's really good. He's been doing it for a long time.
It's like the game Paperboy. I remember it was like on the Super Nintendo.
So that right there I just drew as a function. That matches the definition of function. Surprisingly enough, what I just drew there is 100% a function. It follows all the rules that I set forth in the one above. And let's talk about why it actually is a function. Do you know why it's a function?
The mailman has a purpose.
The mailman has a purpose, but a mathematical function. Not just he has a function in life, it's actually a mathematical function. You could answer this, and there's math classes that just talk about stuff like this, like real-world situations that are functions. This is a function, and if we look down here, it says the act or process of placing each letter in a mailbox is a real-life example of a function. And let's talk about why it's a function. There's things that are acceptable that the mailman can do, and there's things that he cannot do with the mail. We're just talking about one of two things. So, function. Here's where it's good. The mailman is fine if he does this process. So let's say he has 3 letters. That's letter number 1. That's letter number 2. That's letter number 3. And we're going to say this is my domain. What was that?
Should we have drawn a picture?
I would.
Man.
I'm doing it. All right. So we have a function where the letters are our domain. The letters are traveling somewhere. They're traveling to, so let's say these 3 letters are going to go to 2 mailboxes. Two beautiful mailboxes. I'm going to say letter number 1. So let's call our mailboxes our range. Because the mail is actually going somewhere. Our domain gets put into something. That's why we call it the input. It gets put into something. All right, let's say letter number 1 goes to mailbox number 1. Letter number 2 goes to mailbox number 2. Is it okay for a mailman to take a letter and put it in a mailbox?
Yes.
Yes. Is it okay for that 3rd letter in the real world, just think real world, is it okay if a mailman puts 2 letters in one mailbox?
Yes.
Have you ever opened your mailbox and there's 2 letters in it or more?
Yes.
Yes. That is okay in the real world. A mailman can put 2 letters into one mailbox. Now let's see if this still works with the definition of our function. Well, a function is each element of domain is paired with exactly one element of the range. This letter goes to one element of the range. Our second letter goes to one element of the range. And our 3rd letter goes to one element of the range.
But it can't go the other way.
I never said it could go the other way. It cannot.
Oh, okay.
But right now, is this a function? Does each letter go to one mailbox? That's why this is a function. Each letter has to go to one mailbox. Here's where we have a problem, and it becomes a crime. The mailman got a letter that's delivered to 2 mailboxes.
He cuts it in half.
So the mailman, I will cut it in half and put 1/2 there and 1/2 there. Have you ever received half a letter because the mailman wasn't sure where it's going? No. That is A, a crime, and B, it's no longer a function if you could do that. Since you can't do that, the mailman is a representation of a function. Each letter has to go to one mailbox. A letter cannot go to 2 mailboxes. So a mailman delivering letters where letters are our input and mailboxes are our range is an example of a function. You can think of almost every function. You can break it down into letters and mailboxes to see if it works. So that's the way I like to think of domain and range and whether something's a function or not. Your domain is getting mapped to something in your range, just like a letter is being delivered to a mailbox. You cannot map something to 2 places. You have to tear it apart and put it in those 2 places. That's where it's no longer a function. So the function's good as long as I don't rip an envelope. I break it if I rip it in half. Yeah?
So wouldn't the letter be like an equation and the mailbox is the solution? Because like...
Well, the letter, you could think of the letter as being our x value, right? And the mailbox would be our total equation, or f of x. So you input, this is the number you're plugging it in. This is what you get as an output. If you want to think of it x's and that sort of thing. So this is what you'd input. This is what you'd get as a result. So I input this, and now I have a mailbox full of that. All right, let's put this to numbers, though. What exactly is domain? What exactly is range? Domain, and 99% of the time when I say domain, I mean my x values. I will explicitly tell you, hey, your x values aren't your inputs in this one. All right? If no one tells you, it is assumed that I'm talking about x.
So the domain is the letter.
Well, domain will be our x values. Oh, yeah, is our letter. Yeah. Our domain would be x values or our letter. In this case, x could be a certain numbers. When I ask you what is the domain and I give you an equation, I think the easiest way to think about it is what values can't x be? All right, so it's easier to look at how to break it than to look at what all works for it. So if I'm looking at this equation, I'm looking for x values. So what I'm asking is what numbers can I put here? What numbers am I allowed to put underneath that radical and it still results in a real answer? Can I put a -1 in?
No.
Can I put a -2 in? What's the smallest number that I could plug in for x that still works for this and comes out with a real answer? 0. So x cannot be any negative numbers. So we're just looking at x cannot be negative. Since x can't be negative, like was said, it can either be 0 or higher. So we can either say x needs to be bigger than or equal to 0. That's one way to put our domain. Or we can write it like 0 to infinity. Both would be examples of our domain. Domain is what numbers can I plug into x. Once again, domain is what numbers can I plug in for x and still get a real answer out. Our range, on the other hand, is what are all our outputs. In this case is what is our y value after I plug in a number. My domain must be 0 or bigger. Yeah.
Would it just be the same answer?
It would be the same answer, actually. But let's talk about why it'd be the same answer. So we can't plug a negative in here. The smallest number I can plug in for x is 0. The square root of 0 is 0. Since I can't plug negative numbers in, I can't get negative numbers out. So the smallest value I can get out is square root of 0, which equals 0. Anything bigger is going to be bigger than 0. If I do the square root of 1, that's going to equal 1. The square root of 2, that would be, what, 1.41.
So the range is 0 to positive infinity.
0 to infinity as well. So either we can say y must be bigger than or equal to 0, because that's true. Or we can just put, and probably more traditional would be 0 to infinity. Make sure you're using brackets and parentheses correctly. Oh, yeah. But 0 is going to have a bracket around because it can equal 0. A catapult.
Yeah, because like the domain is like you can only put in certain things
Oh, yep.
to like, get the right way to punch it.
Yep. And where does that rock go? There's lots of functions. And a catapult actually would be an example of a function because the rock goes to one location. You don't split apart and hit two different things.
Unless it's like Angry Birds.
Anytime you have to go rationalize why it could be false, just don't go down that route. It is. All right, function notation. The reason why I wrote this is because people get slightly confused with it. There's a whole bunch of information here. A, that F. Don't get confused by F's, G's, H's, smiley, or whatever you want to put in there. This is just the name of the function. F is the name. X tells you what you're inputting. So if I said f of 2, I'd be talking about the function f, and I'm going to plug a 2 in for all my x values. Y is just the output. So if I plug in 2 and I get out 6, 2 is my input, 6 is my output. So 2 is what I plug in, 6 is what I get after I do the work. I think that's the most important part about this one. All right, let's continue on. So we're supposed to determine the domain and range given either lists or equations. With lists, we just have to realize that whenever I have like a point, it's x, y, x, y, x, y. So all of those first numbers, that -2, that 2, that 3, are going to be my x values. So that 2, or that -2, that 2, and that 3, those are all my x values. I guess I'll circle them.
Oh, they're on the pages.
What was that?
No,
This
they're on
is supposed to be
cases.
over here. This is supposed to be. That's what happened.
Yeah,
Yeah.
What happened?
This is 151 and this is 152.
Oh, they must have got it printed out of order. Okay, yeah, we're on 152. Yeah, we're slightly out of order. All right, 4, 7, and 9. The other class didn't say a word about that. Yeah. Maybe they just wrote in the wrong places. They're like, scratching them. All right, so those are my y values. Remember, our x values are our inputs. Our y values are our outputs. So whenever it's listed like this, your first numbers are all of your inputs. So that's my domain. Your domain are all your x values. So to list this, we're just going to put our domain, which you can just put as a cap D after this. Our domain would be -2, 2, and 3. And they use braces, not parentheses. Parentheses tell you it's a range of numbers. Braces just mean that it's -2, 2, and 3. Those are the only possible answers. Our range are going to be all those second numbers. So our range is going to be 4, 7, and 9. That's it. That's my domain. That's my range. I didn't ask you if it's a function or not. It is a function, and we'll do that later on, but all I asked was for the domain and range. All right, our next one's a little trickier. That's why I gave us a little bit of space. I need to find the domain and range. Reminder, domain is what values can I plug in for x? That's all I'm asking is what values can I plug in for x? I'm going to first see if I can break it. So I'm going to plug a -2 in. I have 2 times -2, which would be -4. -4 minus 1 equals -5. Square root of -5, not a real answer. So I know for a fact I can break it if I want to. Since I can break it, there must be numbers that don't work for it. Whenever I see a square root, I'm going to say to myself, I can't have a negative underneath the square root. I can't have a negative under that square root. So this 2x minus 1, the smallest value that can be is 0. So just write the equation out. Well, 2x minus 1 is allowed to be 0, but it either can be 0 or it needs to be bigger than 0. So 2x minus 1 must be bigger than or equal to 0. I add 1 to both sides, divide by 2. We just come up with x needs to be bigger than or equal to 1/2. That's my domain. I could plug 1/2 in and it works. I could plug 1 in, 2 in, 3 in. Those all work. Anything smaller than 1/2, and I break it. So our domain is going to go from 1/2, because it's equal to, I put a bracket, all the way to infinity, because I can put a really large number in there. Yeah.
So would the range just be 0 to infinity because that's the smallest amount?
Yep. Our range is going to be, just like Luke said, 0 to infinity. And think about that for a second. Why is it 0? Well, if I plug 1/2 in, I have 2 times 1/2 gives me 1. 1 minus 1 is 0. I can't get any smaller than that because I'd have a negative number. So y can result in 0 to infinity. Yeah.
So whenever there's a square root, your range will always be 0 to infinity.
Asterisks, but yes. Always is such a terrible word to use.
Most
Most of the time. If you had to err on the side of just putting that down, you'd be right 99% of the time, just putting that 0 to infinity. And absolute value is going to work the same way almost all the time. Because what's the absolute value of -2? What's the absolute value of -100? What's the absolute value of -0.5? What's the absolute value of 1 trillion? Is there any numbers I can't take the absolute value of? No. So what numbers can I plug in?
Every number.
All of them. They all work. Any number works. I can't break it. So my domain, which are my inputs or my x values, must be -infinity to infinity, all real numbers, because they all work. I can plug whatever I want in, and it's going to work. However,
your range is not.
my range is not going to be all numbers, because my range is what comes out, right? What's the smallest value I can get if I take the absolute value of a number?
0.
0, because I can't get negatives out. If I plug a negative million in there, I still get out a positive million. So our range is going to be from 0 to infinity, because you can't get a negative out. Once again, domain is what can I put in? Range is what do I get out afterwards? What's the smallest value I can get out? To what's the biggest? Questions on domain and range besides the fact that it's on the wrong page?
You said you can't break it. It made me think of an episode of The Office where Dwight ties a stroller to the back of his car, like drives around and slams it into stuff to see if he can.
He was just showing that he could break, and he turned out he couldn't.
It was funny.
That was a funny episode. All right.
12,000
Our next one, which should be below it, hopefully it's not on a separate page. Identify the function from a graph. This is vertical line test. This is vertical line test, and let's talk about why it works. Vertical line test. You are just going to put a vertical line all the way through your graph, and as long as it hits one point every single time, it's a function. If it ever hits 2 or more points, it is not a function. So I'm going to tell you right now that first one is not a function. Let's apply that mailman thing to it. So my input, remember our x values are our inputs. So these are our inputs. Maybe I should have put inputs instead of x. I just don't have a ton of room. These are our inputs. And our y values are our outputs. So if we look at that point there, this would be kind of like saying, hey, I have letter, and the x value for it is 2. I have letter 2. Well, that's going here and here. It's going to 2 different locations. 2 goes all the way up to y value being 2, and it goes all the way down to y being negative 2. So a drawing of that might be something like, I have to go to mailbox 2. I also have to go to mailbox negative 2. So I have a letter that has to go to 2 different places, but that means I need to tear it. Not allowed to tear a letter. That is why it fails, and it's not a function. Yeah.
So why did your line that comes out from the vertical line going to the envelope, is it on the 2 just because that's where both of those were, or is there?
It's the y value that it'd be mapped to, about 2. See how this would be the point 2, 2,
Yeah.
and this would be the point 2, negative 2. This is saying letter 2 goes to mailbox 2 and to mailbox negative 2.
I mean, like the black one, like it's in between them. Does that matter, or is it just like?
Oh, why did I call it letter 2?
No, like, is there a reason on like the x-axis the line is on the number 2, or no? Like your black line that you drew that points. Yeah, that one.
Right, that's my input. My input is 2.
Oh.
So I just
okay.
put a point by where my input is, because my input's the x value,
Yeah.
and my outputs are my y values.
Okay.
So that's why I put the dot at 2, because I'm saying my input is letter number 2.
But it comes out with 2 things.
It comes out to 2 things. I have to map that to 2 different. All right, the next one. Well, that just, no matter where I put the line, all the way across there, it only hit 1 point at a time. Maybe I'll circle that 1 point. It's right here. No matter where I put it, that's the most places I can hit. So this is going to be a function. Last one. Is that a function or not a function? Jack says no.
Because there's 2 solution sets. Because it's a union.
Yep.
So, right?
So is it a function or isn't it a function?
It's not a function.
It is not a function.
It's not.
It is not a function because it hits 2 places. Doesn't matter how it's drawn. These don't have to be connected. It doesn't have to look like this.
Because it still can't be in like 2 places at once.
It still can't be at 2 places at once. So this is still not a function because I go to 2 different places. That negative 2 maps to those 2 different places, so it's not a function. Don't overthink the vertical line test. If it is 2 places, not a function. It's 3 places, it's not a function. Don't overthink it. Like I said, in this kind of stuff with functions, if you have to overthink it, you probably did something wrong, and you're going to force yourself to get to the wrong answer. All right, continuing down, we're going to determine if these are functions from either lists or tables. One way you can think about this, and how I kind of do in my head, or I write it down, I'm just going to list my inputs and outputs. So my inputs here are going to be those first numbers. That would be 1, 2, and 4. Our outputs are going to be 3, I'm not going to list that again, it's just 3 and 9. 1 goes to 3, so think about that as being an envelope. Envelope is going to mailbox number 3, that's okay. 2 also goes to 3. Is that okay? I always forget. Can you put two pieces of mail in a mailbox? Yeah, okay, whew. Then we're still okay. And 4 goes to 9. I didn't have to tear any numbers apart. So this is a function. The next one is not correct. If I do the same thing for the next one.
You can't go to -3 mailboxes or 0 mailboxes.
It's just a name. It's the -3 family.
I bet they're really pessimistic.
Oh. All right, let's just write down all of our inputs. Our inputs are 9, 9, so I'm just going to put 1, 9. We put down a 4, and we put down a 0. Our outputs are going to be -3, 3, 2, and 0. Well, 9 goes to -3. That's okay. It's okay if letter 9 goes to -3. Unfortunately, 9 also has to go to 3. Can an envelope go to 2 different mailboxes? No. You don't have to go any further than this. Right here tells you it's not a function. Yeah?
So you just can have 2 x variables are the same?
Mm-hmm. Yeah, the y's have to be different, though.
Okay.
So what Aaron and I realized is that, hey, I have a 9 here and a 9 here. It's going to 2 different locations. So it's a good thing to recognize that if you have 2 of the same inputs, as long as both these outputs are different, you're good. However, I can trick you. Not really tricking. Kind of is. I could do that. 9, 3, 9, 3. All I'm saying is letter 9 goes to mailbox number 3. Letter 9 goes to mailbox number 3. It's okay if I say it twice. The same thing's happening. That would be a function. Right now, this would be a function. As soon as I bring that negative back out, not a function. All right, our next one. Look at it, think about it. Tell me whether it's a function or not a function. I'll give you just a second. I want everyone to look at it and ask yourselves, is it a function or is it not a function? And I'm saying that for a reason, because it's one of those that you can mess up in your head.
I don't understand what you're asking.
Is it a function or is it not a function?
Well, this price table doesn't make sense, actually. Yeah.
Well, I shouldn't have to tell you what's the input and what's the output, because, and why I don't need to tell you, you need to know what the quantity is to determine the price. So that's what makes it our input. You have to know this before you know the price. So you already know what's your input, what's your output.
So this is a function.
Is this a function? Jack, you had your hand up first.
It is not a function.
It is not a function. Why is it not a function? Luke?
Because 1 through 5 and 5 through 10 both contain the same x value. It goes to 2 different numbers.
5 goes to 940. So if I have 5 items, I either pay 940 or I pay 875. Does that make sense?
Pick your poison.
Yeah, pick your point. I picked 875.
That's sneaky.
Not a function.
If it was 1 through 5 and 6 through 10.
10, then it would be a function. It could be 1 through 5 and then 5.00001 to 10. Or we could have used parentheses. Parentheses would have solved that too. If I said, if I did this, 1 through 5, and then 5 through 10, I would be fine there too.
Wow.
So just be careful. Ask yourself, does that get mapped to two different places? And in the real world, it doesn't make sense either. That's why functions really apply to real world aspects. That wouldn't make sense if you ran a store and you're just like, if you bought 5, you choose what you pay. All right, now we're back to the other page. But this is going to go really quick. So just remember, F is just the name. G is not just the name. So as soon as I see this, all that F is telling me is which one of these to use. All right, it's telling me to use this f of x equals x squared minus 2. But what I want you to realize with that f of 2, that f of 2, that 2 is replacing your input. Your input is now 2. Since my input is 2, I'm going to change all of those x values to 2's. So rather than going x squared minus 2, I'm going to do 2 squared minus 2, which is 4 minus 2, which equals those. Same thing on the next one. Even though there's more inside of it, everything that's in this g of whatever, that is my input. So I'm going to replace every x value that I see for g of x with x minus 2, which is going to look something like this. 2 times x minus 2. I leave it in parentheses because it's the whole quantity. Minus 3. Well, that's going to be 2x minus 4 minus 3, which is going to be 2x minus 7. There is no solving these. There's just simplifying them. So there's ones in your homework that are going to have x squareds in it. Don't plug it in the quadratic formula because that only works if it's equal to 0. All you have to do is simplify. Plug in and simplify. If it comes out to one number, then awesome. If not, just leave it as is. All right. G of x plus h. Once again, I don't care what's in there. This could be smiley face rainbow. All I'm going to think is that's my input. Replace, since I replaced x with x plus h, I'm going to replace x plus h with the x on the other side. So that's going to be 2 times that x plus h minus 3, which only simplifies down to 2x plus 2h minus 3. That's it.
And D is as simplified as it gets.
Kind of. So D is a little weird. D is saying g of x equals 5. Do they tell us what our x equals in that one? So what they're telling me is the output equals 5. So let me rewrite what g of x equals down below it. Sometimes that makes a little more sense.
Would x be 0?
Let's see. So I have g of x equals 2x minus 3. Note here it says g of x equals 5. So what that means is I'm going to replace that 5 with all of g of x. I'm saying anytime I see g of x, replace that with 5. The ones up above, we're saying anytime you see x, replace with what's inside of there. This one says replace g of x with 5, so that's what I'm going to do. 5 equals 2x minus 3. I would add 3 to both sides, so I have 8 equals 2x.
So this one you can solve.
This one you can solve with x equals 4. And let me just real quickly talk about what that means. What I'm saying in that bottom left-hand one, if x equals 4, what I'm saying is if I input 4 and I run it through the cycle or whatever needs to happen, I should get out 5. So if my input is 4, I should get out 5. So that means if I replace in g of x that x with 4, which would be 2 times 4, which equals 8, minus 3, it should equal 5, which it does. This is saying input 4, get out 5. that one's a little bit different because they're telling you what you're going to get out. You have to find out what you have to input. All the rest of them are where they gave you an input. You have to figure out what your output is. All right, input versus output. These are generally the harder ones for people to see. But as long as you do what I just did and you practice it, you'll be fine on that. Questions? Yes?
So if you give us like an entire equation, like g of x equals something x squared minus or plus something x, whatever, and then we got like that equals 5, could we pull 5 to the other side and use the quadratic formula and just like...
Mm-hmm.
Okay.
So you'd say 5 equals x squared plus whatever. You subtract 5 from both sides and get it equal to 0, then you could solve it.
Awesome.
Yep. If you know an output, most of the time you'll get down to a number for your input. Other questions?